Hey there, and welcome. Today, we're going to dive deep into the periodic table, to a family of elements that, and I mean this literally, builds our world. We're talking about the transition metals.
It sounds like the start of a riddle, doesn't it? But believe it or not, the answer connects some of the most fundamental materials of, well, our entire civilization.
Yep, you guessed it. The insane strength of steel in that skyscraper, the timeless value of that gold coin, and even the brilliant blue color you see in that beaker. It all comes down to the unique chemistry of this one special family.
So, to really get a handle on just how important these guys are, we've got to take a little trip back in time. Because these elements aren't just useful today, they are literally the foundation of human history.
I mean, just let that sink in for a second. We're talking about the materials that gave entire ages of human history their names. The Bronze Age, the Iron Age. Their influence is just massive.
So what's the big secret? What makes these metals so darn special? Well, for that, we have to zoom way, way in, right down to their atomic blueprint.
And here we have it, the key that unlocks everything. It all comes down to this one little detail, an incomplete D subshell. Now I know, that sounds super technical, right? But trust me, that one phrase is the secret sauce behind all of their amazing properties.
Okay, let's break this down with a quick comparison. It makes it way clearer. Over on the left, you've got scandium. See how its D shell has just one electron? It's incomplete. That's a textbook transition metal. But look at zinc on the right. Its D shell is packed with 10 electrons. It's completely full. So get this, zinc, which we all think of as a classic metal, doesn't technically count as a transition metal by this strict definition. Kind of wild, right?
So here's the bottom line, the thing you really need to remember. As you move across the periodic table, these elements do something a little weird. Instead of just adding electrons to their outermost shell, they start tucking them away into an inner shell, this D shell. And that tiny little quirk in their design, that's the key to, well, everything. Okay, so we've got this weird electron setup. What's the big deal? How does it actually play out in the real world? Well, it's not just some abstract chemistry fact. It gives these metals a whole spectrum of what you could honestly call superpowers.
Okay, superpower number one. These things have multiple identities. Because those inner d electrons and the outer electrons are so close in energy, the atom can lose different combos of them. And what does that mean? It means they can take on all sorts of different identities when they're in a chemical reaction.
And I mean, just look at this chart. While most elements are stuck with, one or two choices, these transition metals are total chemical chameleons. And the absolute star of the show here is manganese, right in the middle. Look at that. It can have any oxidation state from +2 all the way up to a whopping +7.
All right, on to superpower number 2. These metals are just incredibly tough. And you know that sea of D-shell electrons we were talking about? Well, they don't just mess around in chemical reactions. They also form these super strong bonds between the metal atoms themselves. And that's what gives us all those classic properties we think of when we hear the word metal. They're hard, they have incredibly high melting points, they can be stretched and shaped without breaking. It's no wonder this is the stuff we use to build basically everything important, from massive bridges to powerful jet engines. But it's not all about brute strength. These metals have an artistic side too. A lot of their compounds are just stunningly beautiful. So what's the deal? Why are they so colorful? Well, the answer is basically an electronic light show happening at the atomic level. The electrons in those half-full d orbitals can jump around, and when they do, they absorb specific colors from the light that hits them. So the gorgeous color that we see, that's just the light that's left over, the light that gets reflected back to our eyes. How cool is that?
And for our last superpower, you guessed it, it's also a direct result of those amazing d electrons. Turns out, a lot of them have some pretty strong magnetic personalities. It really all boils down to one thing: unpaired electrons. See, when an electron is all by itself in an orbital, it acts like a tiny little magnet. This makes the whole atom get pulled towards a bigger magnet. We call that paramagnetism. And guess which elements are packed with these lonely unpaired electrons? Yep, the transition metals. Okay, so we've seen their atomic-level superpowers, but this isn't just about cool chemistry trivia. These unique properties are what make transition metals some of the most useful, most critical elements in our world, period. You can think of them as the ultimate team players. They act as catalysts to speed up reactions, they form alloys to create brand new materials, and they build these incredibly complex compounds that we use for a ton of industrial applications.
Let's look at a perfect example of how they work as catalysts. Check out how iron uses that chameleon-like ability to switch identities. It flips from a +3 state to a +2, and then right back again. In doing so, it helps the whole reaction move along, but it doesn't get used up itself. It's this beautiful, efficient little chemical cycle.
And it's not just about reactions. It's also about making materials stronger through alloys. Their raw physical strength makes them perfect for mixing and matching. You take iron, you mix in some chromium, and boom, you get stainless steel, a material that is way, way better than either of its parts alone.
But just when you think you've got it all figured out, chemistry throws a curveball. There's a final twist that kind of messes with our neat and tidy definition.
So let's talk about silver. Everyone knows silver, right? A classic transition metal. Or is it?
If you look at a neutral silver atom, you'll see its d shell is completely full, just like zinc. So, at first glance, you'd say, nope, not a transition metal. But remember that fine print in the definition? Or in its ions? Well, when silver forms a common ion, it loses electrons, and suddenly its d shell is incomplete. So it qualifies on a technicality. It's a classic little paradox that shows just how precise these scientific rules really are.
You know, from the dawn of the Iron Age to today's green energy revolution, these incredible elements have always been at the very heart of human innovation. It really makes you wonder, doesn't it? With all this amazing versatility coded right into their atoms, what massive global challenges are transition metals going to help us solve next?